Hi, we are Team 8059A and this is our Annotated Programming Skills Challenge. In our video, we'll first be going over our skills round, then our design, and finally, we'll take a look at our code. We have two tracking wheels, 2.75-inch Omni wheels connected to encoder sensors and positioned around the robot. These help us measure more accurate values than the motors, as these wheels are rubber banded downwards, and as such are always fully in contact with the surface of the field. Additionally, we have a horizontal tracking wheel at the back of the robot to track lateral movement. Due to the use of Omni wheels, our robot is prone to strafing, which this tracking wheel will account for. We also use a vision sensor to detect the position of the red balls so that we can intake the balls regardless of small discrepancies in the field. A light sensor is used to detect whether or not the ball is in the ideal position for shooting, allowing us to get the ball into the same position consistently for consistent shooting.
The base library makes use of 3 asynchronous tasks to achieve precise base movements. Data from the encoders are first passed into base odometry. This task regularly updates the robot's X and Y position as well as bearing on a virtual Cartesian plane. Over the refresh rate of 5 milliseconds, it can be assumed that the left and right wheels travel at constant speed. As a result, distances traveled by two sides will follow two arcs of similar angular widths of two concentric circles. Additionally, we use a lateral encoder to account for any movement on the horizontal axis due to strafing. Using trigonometry and geometry, the change in x-coordinate, y-coordinate, as well as bearing is calculated. The base control task uses the locational data calculated by the previous task as well as target encoder values passed in from base movement functions to calculate target power values for the base motors. This is done using a PD loop for increased accuracy and consistency. Note that this task only calculates target powers and does not directly set power to the motors. In order to combat issues like skidding and friction in the real world, the target power values would have to be passed through base motor control. This task serves the purpose of capping power values that are going out of the specified bounds, as well as implementing motor ramping, which prevents sudden increases in motor power to reduce skidding. The vision library, on the other hand, uses the V5 vision sensor to position the robot relative to a specified field element with the aid of 2 asynchronous tasks. Data from the vision sensor is first passed into object odometry. This task regularly updates the on-screen coordinates as well as width and height values of the closest red ball in order to determine the position of the ball we want to intake and the closest blue ball to determine the position of the goals we want to score. Vision base control then processes vision base move functions into move and turn components using the currently tracked signatures width and x values respectively. These powers are then passed through a PD loop before finally getting converted into raw power values for the left and right side of the base. The x and width values are chosen instead of y or height due to better accuracy and consistency. In order to ensure that the two libraries interact seamlessly, a global trigger named useVision is used to keep track of which asynchronous task is currently controlling the base motors. Odometry code functions normally until useVision is triggered. In this event, base control and base motor control stop running to allow the vision library to control the base motors. Base odometry still runs in the background in order to maintain global absolute position upon the completion of the vision task. The target encoders are reset to the current encoder values so that normal base control can resume. This cycle is then repeated when the next vision function is called.